Okay, hi guys, so we'll be continuing on seeing more on the adiabatic process. So for an ideal gas, we saw in the previous lecture that P, or rather T v to the power gamma minus 1 is constant. Okay, so continuing from that, so T can be written as PV divided by some constant. I'm writing NR as some constant K times v to the power gamma minus 1 is constant. Okay, so we can write here that P v to the gamma is a constant in adiabatic process. Okay, now let's see for the same in terms of pressure and temperature. So this is in terms of pressure and volume. So in terms of pressure and temperature, we can write that we know that T v to the power gamma minus 1 is constant. Okay, so from here we can substitute the value of V from the ideal gas equation, which is nRT, which is nR I'm writing as some constant K divided by P to the power gamma minus 1 is constant. So from here I can write that this is nothing but T to the power gamma multiplied with the P to the power 1 minus gamma is some constant. Okay, so now let's just raise this term to the value or to the power of 1 upon 1 minus gamma. Okay, and raising the RHS also to RHS is a constant term, and raising that constant term again to the power of 1 upon 1 minus gamma would also be some constant term. So from here we can write that P times T to the power gamma divided by 1 minus gamma is also a constant. So these are the various relations we can get from a adiabatic process. Now let's next see what happens in an irreversible adiabatic ideal gas expansion and compression. So we will be seeing irreversible adiabatic ideal gas expansion or compression. Okay, so we know that du is equals to q plus dw, rather dq. So dq is 0 in an adiabatic process, so we can just write that du would be equals to dw, or from here we can say that delta u would be equals to w, or change in internal energy would be equals to work done. So let's see this case by case. So first case is free expansion. Okay, so in free expansion we can write that P external would be equals to 0 and work done would also be equals to 0, and we already have the adiabatic process, hence Q would be 0. So from here we can write delta U, which is du plus dq, both work and heat exchange is 0, so change in internal energy would be 0, and delta H is again delta U plus P delta V. P delta V would again be 0. Okay, and as a result we already have delta U as 0. So rather this term would be 0. Why? Because P external is 0. There would be some delta V, but as the gas is expanding, so there would be delta V, but P is 0 because it is free expansion, so delta H would again be 0. Okay, and for an ideal gas, again free expansion would be 0. Why? Because there is no change in temperature, hence delta U would be 0. Why? Because U is a function of temperature in case of ideal gas. Okay, now let's see case number 2. So in case number 2, we know that NCVM delta T is equals to minus P external dV. So rather this is dt, not delta T, dV. Why are we writing this? Because we know that as du is equals to dq plus dw. In case of adiabatic process, dq would be 0, hence du can be written as dw, and for an idle gas, du can be written as ncvm dt, and dw can be written as minus p external times dv. Okay, when we integrate it, we see that it would be ncvm delta t would be equals to again minus p external times delta v, which can be written as minus p external, it would be v2 minus v1. Okay, so we can write that ncvm t2 minus t1 would be equals to minus p external. What would be v2 minus v1? v2 minus v1 would be simply nr t2 upon p2 minus nr t1 upon p1. Okay, so from here we can write that simply the n can get cancelled out. Okay, and we can write that cvm t2 minus t1 would be equals to minus p external times gas constant, which is r, multiplied with t2 upon p2 minus t1 upon p1. Okay, so this is very important as far as irreversible adiabatic idle gas or idle gases are concerned. Okay, this is a very important equation. Okay, where again to reiterate, P1 is initial pressure and P2 is final pressure. Okay, and P external would be equals to P2 in complete expansion or compression process. Okay, next we see that in an adiabatic process, T of irreversible process is greater than or would be greater than T of reversible process, and this is always valid. Okay, always valid means whether it's expansion or compression. Okay, so just to draw a graph, then we can draw it something like this. That let's have compression on the positive y-axis and expansion on the negative y-axis. Okay, so this is the line for T reversible in case of compression, and this would be the line of T irreversible. Okay, so in this case T irreversible would be definitely more than T reversible, and on the below side we have T irreversible here and T reversible here. So again T irreversible is more than T reversible. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing more on the expansion and compression of gases in adiabatic conditions. So till then, good luck and goodbye.